All right, welcome back. Today we're going to talk about the calculator in your computer. We're diving deep inside that machine on your desk to answer a really simple question. How does a box of metal and silicon actually do math? It really feels like magic, but I promise you, by the end of this, you'll see it's all about one brilliant, simple idea. I mean, really think about it. Your computer can crank out millions of calculations in the blink of an eye. But how? It doesn't have fingers, there's no abacus inside. It doesn't have a brain like we do. So how on earth does this box of wires actually add, subtract, and do all the other math we ask it to? To get to the bottom of this, we have to go on a bit of a journey. We're going to peel back the layers of the computer, kind of like an onion, going deeper and deeper until we find the one tiny component that makes all of this possible. So first up, you've got the computer case, right? The box you see on your desk. Pop that open and you'll find the motherboard. It's kind of like this central nervous system connecting everything. And sitting right there in the middle of it all is the star of our show, the microprocessor. You can just think of it as the computer's brain. Now this brain, this microprocessor, is absolutely jam-packed. We're talking billions of tiny little parts. But here is the secret, the absolute key to everything. All of that incredible power, its ability to do complex math, it all comes from billions of copies of one single, incredibly simple component. And that component is the transistor. Seriously, for a moment, forget everything else. The transistor is arguably the most important invention of the 20th century, and it's the only building block we really need to understand how a computer calculates anything. So what the heck is a transistor? Well, at its core, it's just a switch. A really, really microscopically tiny switch, but it's a special kind of switch. Instead of flipping it with your finger, you use a tiny pulse of electricity to turn it on or off. And get this, that tiny electrical pulse then controls a much stronger flow of electricity. It's literally a switch controlled by electricity itself. Think about a normal light switch. It has moving parts, it makes a clicking sound, and eventually it wears out. A transistor, on the other hand, has zero moving parts. None. This means it can be flipped on and off billions of times a second without ever wearing out. It's basically the perfect switch, silent, durable, and unbelievably fast. Now, a single switch is useful, sure, but the real genius, the real magic, happens when we start combining them. By wiring transistors together in clever ways, we can create something way more powerful, circuits that can actually make simple decisions. We call these logic gates. Let's start with our first example, the OR gate. Imagine you have two switches, A and B, and they both control one light bulb. With an OR gate, if you flip switch A or switch B, the light turns on. If you flip them both on, hey, even better, the light is on. It's a pretty easygoing circuit. Now let's look at the AND gate, which is a lot stricter. As you can see here, the light will only turn on in one very specific situation, when input A and input B are both on at the same time. If even one of them is off, you get nothing. Zip. Nada. So, we have these switches and gates that can only be in one of two states, on or off. Well, this simple two-state system is the foundation for the native language of every single computer on the planet. And that language is binary. In the world of binary, everything, and I mean everything, is represented by just two symbols. We use 0 for the off state and 1 for the on state. This is the crucial link, you guys. Those logic gates we just looked at, they're not just controlling electricity. They are physically speaking the language of zeros and ones. So, how do we actually read this language? It might look a little weird, but it's pretty simple. Each position in a binary number has a value. Starting from the right, the first spot is worth 1, the next one over is worth 2, then 4, then 8, and you just keep doubling as you go. To get the total, you just add up the values for any position that has a 1 in it. That's it. Okay, now this right here is the most important rule for this entire explainer, so lean in. In binary, 1 plus 1 does not equal 2. It equals 1, 0. Now, I know what you're thinking, but stay with me. It's just like our regular math. When you add 9 plus 1, the ones column is full, right? So we write a 0 and carry the 1 over to the tens column. Binary works the exact same way. Its first column can only hold a 0 or a 1. So when you add 1 plus 1, that column is full. You have to write a 0 and carry the 1 over to the next column, which is the twos column. So 1, 0 in binary is really 1, 2 and 0 ones. This little rule is the key to everything. So now we have all our pieces. We've got our transistors acting as switches, we've got our logic gates making decisions, and we have binary, the language those switches speak. It is time to assemble our building blocks and build a circuit that can actually do math. We're going to build an adder. And this shows you exactly how it's built, from the bottom up. At the very bottom, you have your basic transistors. Groups of those form logic gates. You combine those gates to create simple half adders. And then you can combine 2 half adders to make a full adder, which can handle that whole carrying the one thing. It's all just layers of simple switches arranged in clever ways. So what if you need to add bigger numbers? Well, you just chain these adder circuits together. When one adder calculates 1 plus 1, its result is too big, so it sends that extra 1 over to the next adder in line through a special carry wire. This is exactly how we all learned to carry the 1 in grade school, except it's happening at nearly the speed of light. Okay, so let's zoom all the way back out. What we've just built together is the fundamental calculator that lives inside your computer. But here's the kicker. It's not just one of them. There are millions, all working together in perfect harmony. It's like a symphony of logic. Inside that little microprocessor, there are circuits just like the one we designed, performing millions, sometimes even billions of these simple additions every single second. This incredible speed and massive scale is what turns simple on-off logic into the powerful computers we use every day. And it all just boils down to this one elegant, beautiful concept. There are no tiny gears inside your computer, no little moving parts, just the simple, profound idea of using electricity to control the flow of other electricity. That right there, that is the engine of the entire digital world. So I'll leave you with this final thought. We've just seen how arranging a bunch of simple switches can teach a machine to do math. But that exact same principle, just arranging switches into complex logic, is how computers do everything else, from playing music to connecting us across the globe. So if we can do all of that just by flipping switches, what else can they be taught to do?